two special cases of charge entering the magnetic field have already been covered, and now we are going to consider the case when entry is oblique. When you say oblique, it simply means that it is neither along the field nor perpendicular to it. You see, the magnetic field is this way, and a charge is entering at an oblique direction. Suppose the angle is theta, this is the velocity of the charge. Charge is plus q. In entire magnetism branch, when we consider the term charge, it simply means positive only. If I want to convey that charge is negative, I'll have to mention it. Unless it is mentioned, it is never considered negative charge. All the rules are meant for positive charges. You want to get the value or the result for negative, you have to simply reverse the result. You see, charge has entered here, and you have already considered two cases. One, when the charge enters parallel, other when the charge enters perpendicular. Both the results also, in parallel or anti-parallel entry, there is no effect on the motion of the charge, and in perpendicular entry, the circular motion starts. Here, none of the two is considered, but you see this has inherent two directions. One is v cos theta and the other is v sin theta. Once you resolve the vector, that mean vector is no more there. So you are having two components. You might say there are two velocities, one parallel to it, the other perpendicular to it. Parallel component, this v cos theta, is going to take the charge undeviated along the same direction, means v cos theta will continue it moving along the field, whereas this v sin theta will cause the circular motion. There is going to be superposition of both the effects, that's a straight line path and circular path. If you combine, you can easily understand that circular path and it has to proceed along a straight line also. As a result, it's going to be helical path. So, as a result, you are having here the helical path this way. V cos theta has taken it along the field, perpendicular component has produced circular motion. The radius here will be given by, it's here you see mv sin theta upon qb. Why v sin theta? Because in place of v, we are having effective component responsible for circular motion is v sin theta here. That's why v sin theta has replaced v. Now, if you want to find time period or the value of omega, this will be 2 pi m sin theta upon qb, and for omega is 2 pi upon t. This will be qb upon m sin theta. This was oblique entry and the resultant path being helical. You got the result. Then magnetic force and Lorentz force, most of the time by newcomers, you see, it is just intermingled, but both are entirely different. Lorentz force is the common term for the presence of electric and magnetic, both the forces. If only electrical force is there, you simply say it's electrical. If only magnetic force is there, you simply use the term magnetic. But when both the forces are there, only then this term would be appropriate. That's Lorentz force. So don't confuse it with any single force. Suppose the two fields are there. In that case, you're going to have electrical force and also the magnetic force. Both the forces are there. But for finding the direction, you have different criteria. The electric force is always in the direction of the field, whereas the magnetic force depends on velocity and field, both as well. Anyway, by adjusting the direction or the angle between velocity and the magnetic field, you can change or affect the direction of magnetic force. You just imagine a wonderful situation in which if you could create the two forces, that is electrical and magnetic, both in the opposite direction, they are going to cancel the effect of each other. And when two forces are cancelling each other, naturally there is no force left to disturb the charge. So in that case, if both the field are there, both the forces are there, but they have cancelled each other, the charge entering the field, the combination of both the field, the charge will pass undeviated. This is very interesting situation. I'll just try to depict with the help of a diagram. You just imagine that there is a magnetic field that's normally inward. To represent this kind of field, you always use the cross. And also, let's suppose that there is electric field vertically downward this way, and charge, as I told, is positive, that's entering the magnetic field. This is a positive charge this way. The velocity. You see, left hand rule again, I'll repeat: father, mother, child, force, magnetic field, and current. The field here is normally inward this way. Velocity is along the middle finger, you see. This is velocity. Magnetic force is going to be this way. That's along positive y axis. This becomes the magnetic force. For electric force, you are already aware that electric force is always in the direction of electric field. So, this is going to be the direction of electric field. Now, by varying or by changing the value of these quantities which are in your hand, in your control, you could manage that thing. You can bring the situation Fm equal to Fe. Direction wise, you are satisfied that both are opposite here. Simply you have to maintain that two become mathematically also equal. In that case, when you say Fm equal to Fe, that means QVB, it should be equal to QE. Q gets cancelled and you get one final condition, that is V equal to E upon B. If this condition is satisfied, you see, both the forces will be there, but no common effect, combined effect. Charge will pass undeviated along the same direction.